So good afternoon, everyone. I am Giusy Spacone, and today I'm presenting the work of our group with the title A Parallel Ultra-Low Power Silent Speech Interface based on a wearable fully dry EMG neckband. I would like to start with an introduction. So what are silent speech interfaces? They can be defined as a novel form of assistive technologies, whose aim is essentially to provide speech without producing an actual sound. You might wonder why such interfaces might be useful. So they can be used to develop novel human-machine interfaces, but also to restore speech for individuals with speech impairments. Also, they can be used to detect the speech in conditions where there is a lot of noise, so audio doesn't work, and in all the conditions where privacy wants to be kept. There are different sensing modalities that we could use to do such a task, but a promising one is represented by surface electromyography. In a nutshell, what we do with surface electromyography is that we capture the transmission of electrical signals from the brain to the muscles. In this case, all the muscles which are involved in the speech production. There are several advantages in using such sensing modality, but in particular, it is extremely useful because it is non-invasive, and it can also be used to detect the speech with an early onset, meaning that essentially we detect the muscle movement before the sound can be actually produced. Given this potential, there are previous works which have already employed surface electromyography for this task. The very first one was presented by Kapoor et al. It's called Alter Ego. It's the interface that you can see here in the figure. And they proved to show the discrimination of 10 different classes with 92% classification accuracy. However, in their system, as we can see, is still quite obtrusive, and they still rely on wet electrodes, which are not really suitable for wearability. In a follow-up work, Liu et al. Developed some tattoo electrodes that could be placed on the face. The solution is still promising, but it still has the limitation of having the placement on the face, and also they were using an acquisition electronics that was rather bulky and not wearable. Finally, last year, Wu et al. Presented the first solution that moved the placement from the face to the neck, achieving a classification accuracy up to 93%, but with a system that still relies on wet electrodes for the reference and the bias, and also tested only on vocalized, but not on silent speech. Hence, the goal of this work is to present an ultra-low power, wearable, fully dry, silent speech interface, which meets the wearability and ultra-low power criteria, and that can be used to detect speech, both in a vocalized and in a silent setting. I would like to start by presenting to you the interface that we designed. It is based on a wearable neckband that I would like the pleasure to show, if you're interested afterwards, with 14 EMG electrodes. We are using a differential configuration to suppress noise, plus 4 electrodes which serve as a bias. This is an example of the necklace worn by an healthy subject together with our electronic. For the electronic, we use the BioGAP platform. It's a state-of-the-art platform developed in our group, which features an NRF53 microcontroller, which essentially handles all the BLE communication, together with a dedicated shield for EMG acquisition. We can collect up to 32 channels, so 16 in a differential setting. And a great advantage is, of course, the ultra-low power consumption of our system. So it's around 22 milliwatts for data collection and BLE streaming. We then wanted to validate our interface. So we developed a data collection protocol, asking the subject to pronounce 8 different HMI-related words. So up, down, left, right, forward, backward, start, and stop. We collected data into batches, and each batch contained 20 repetitions of each word, which were prompted using a GUI in a randomized manner. 7 batches composes what we define as one acquisition session. And between batches, the subject was given some time to recover and to prevent muscle fatigue. We collected a total of 3 sessions, and in between sessions, we were removing the neckbands in order to emulate what would be a real-life use case. We conducted 2 experiments. So one was the vocalized EMG experiment, and another one the silence, meaning that the subject was asked to move the muscles, but without actually producing any sound. Our final dataset consists of almost 3,360 utterances, so repetition of every single word. We started as a first validation with a very simple processing pipeline. So the raw data are, first of all, filtered, and then we window the signal using 200 milliseconds of length. Finally, we extracted features both in time and frequency domain, and we trained a random forest classifier to predict the 8 different words. We conducted 2 different analyses. The first one is a classic five-fold cross-validation. So what we did, essentially, we took the data from the 3 acquisition sessions, stacked them together, and then shuffled all the data. We then consider 4 folds to train and 1 fold to validate. And we repeat over all the different folds. We did this analysis essentially because we wanted to have a baseline with our work, but also we wanted to compare the performances with respect to previous studies, which didn't tackle the problem of repositioning. So, of course, we wanted, first of all, to be comparable with other works. In a second analysis, we did what we call an intersession approach. So, essentially, we trained the model with data from 2 sessions, and then we test on the remaining one. And we do this in a 3-fold setting scheme. So we use, for example, the second and the third test on the first, and then we do this also for the other combination. I would like now to present some of the results that we obtained, starting, first of all, from the first analysis, so the aggregated one. In this graph, what you can see is the classification accuracy reported for each one of the words that we were trying to classify. And we obtained an average accuracy of 87%. Now, if we compare these numbers with previous work, we are, let's say, quite aligned. And we need to consider that in the previous studies, they were relying on wet electrodes or dry plus wet electrodes for reference and bias, which of course makes the problem quite simple because having a stable bias electrode simplifies the problem and ensures better SNR. But of course, is not really suitable for wearable development. These are, on the other hand, the results for the silent experiment. So here we achieved a classification accuracy of 68%, and we try to understand why the silent setting is worse compared to the vocalized one. First of all, we assume that EMG signals acquired in a vocalized setting are way weaker. The SNR seems to be higher. And we also observed that there is some practice needed from the subject to pronounce the word without emitting any actual sound, because this is something that we are not really used to do, at least as healthy subjects. We now move towards the results of the second analysis, which is the intersession approach. In this case, the results for the vocalized EMG, as you can see, are way worse, with a 64% classification accuracy. However, if we look at the per class classification, we are well above what would be a random guess, which would be 12%. And here we also observed quite a nice standard deviation in our results, which really highlights what are the challenges introduced by repositioning the sensors, because even small displacements or changes in the skin conductance can alter quite significantly the results. For the silent speech, the average accuracy is 54%, but something that we found quite interestingly is that the standard deviation seems to be way lower compared to the vocalized experiment. And we would like to have further investigation on why this actually happened. So in conclusion, in our work, we developed the wearable neckband for EMG-based speech decoding with 14 differential channels powered by BioGAP Ultra and with only 22 milliwatt of power consumption. We validated our interface in a realistic scenario with HMI-related commands, achieving 83% classification accuracy, with results perfectly aligned with previous studies, however, with a setup that is fully wearable and can be potentially used already now in a real-life use setting. We also explored for the first time the problem of sensor repositioning that we aim to address in future studies. So what's coming next? First of all, we would like to increase the number of electrodes, so increase the channel count, because we assume that this might help to have more information and also to solve the problem of sensor repositioning. Also, we are already planning to introduce additional sensing modalities, in particular IMU and wearable ultrasound, to have some complementary information. Finally, we plan to develop our pipeline on RISC-V pulp-based microcontroller, which are developed in our group, and finally, extend the data collection to a large cohort of subjects. In this case, only one subject was involved, but we want to provide larger statistical analysis and eventually provide a dataset to the community. With that, I would like to thank you all for your attention, and all the hardware that was used in this work is open source, so you can scan this QR code to have access to the repo and what has been used. Thank you again.